Okay, so now we are doing the event rate calculation. A very yet another example for array. Array is important. So event rate calculation. I am considering a 28 silicon beam. The lab energy is 70 MeV. Charge state is 7 plus. Okay, and the current is 70 nanoampere. And the target is 12 carbon target. And target specification. This is a thin target. 50 microgram per centimeter square. This is the thickness. Now, it is possible that before doing the experiment, we can consider just 28 silicon beam and this much target and estimate the cross section of the nuclei which will be produced as a result of this compound nuclear reaction. Now here I have used the software Pace Force. You can also check this yourself. This is software which is freely available. If you use this and if you put the specifications of target and projectile, then a large number of residuals will be produced, and my nucleus of interest here is 35 chlorine, and Pace Force prediction shows that the cross section will be around 350 millibar. Okay, now before doing the experiment, I am trying to see how much data I can collect using say a 8 clover detector array. This is what I want to do. This is known as event rate calculation. So here I have used the 8 clover detector array. Again, the distance is 5 centimeter. 25 centimeter. Approximate radius of a clover detector is 5 centimeter. The intrinsic efficiency here I have considered the work of Dushit et al. Neve 1999, and here the efficiency is 0.2, and if you do this you will see P comes out to be this. Okay, so P is equal to solid angle into intrinsic efficiency. This is the stuff. Now the coincidence efficiency is, we have done this previously, 8P2 into P square. So I have considered 2 coincidence, 3 coincidence, 4 coincidence, and this is the value. Okay. Okay, so we have found the efficiency of detection. Next, we are trying to find the number of gamma rays produced in the target during the reaction. So it consists of 3 parts, small calculations. Number 1 is number of beam particles incident on target per second. Remember, beam, how much was it? 70 nanoampere. Nanoampere divided by the charge state, 70. So it comes out to be this. Next, number of target atoms per second. So Avogadro number into the thickness of 12 carbon divided by mass of the carbon. This is the number. Next, gamma multiplicity. That means number of correlated gamma rays. Now we are talking about mass 40 or so. So it has been observed that here the gamma multiplicity or number of correlated gamma rays in this mass region is around 6. So I have taken this number. So if I multiply these 3, then I will get the number of gamma rays produced in target, and that is 3.3 to 10 to the power 5. Now if I multiply this number with the previous calculation of efficiency, then I get the total number of coincidences per second is approximately 46. So this is how you estimate number of coincidences in an experiment. I can also give this in an examination, right? So how suppose I change the thickness of the target, say from 50 to 250. Okay, I change the current to 70 to 170 nanoampere. So you have to understand how things are flowing.
So throughout your experiment, 46 খানা করেছেন, 46 খানা কমন
Approximately. So this is what I expect before doing the experiment. So I expect per second this number of coincidences, which is not bad. See, we have talked about 8 clover detectors. Basically, this was used in INGA array, Indian National Gamma Array. Now, again, instead of the 8 clover detectors, suppose we use the GDA array and IUAC, which has got 12 detectors. And these are the specifications. So the radius is approximately 2.5 centimeter. Distance source to detector distance is 18 centimeter, and efficiency is much small. See. So if we use that and calculate the coincidence efficiency, doubles, triples and quadruples, then this is the value. So if you multiply it with the number of gamma rays produced, you get the number of coincidences per second, approximately 2. See, in case of 8 clover array, we were having 47, approximately 50, and here it is approximately 2. So just having more number of detectors doesn't help. The intrinsic efficiency, this is very important. And this overall defines the total number of coincidences along with the number of gamma rays produced. And regarding correlated gamma rays, say for example, suppose we have got a nucleus. Tell me. So this is say gamma A, gamma B, gamma C, gamma T. This is gamma E. This is gamma F. Okay, another. This is gamma G. This is an example. Now you just tell me how many correlated gamma rays, maximum number can you observe? See, if I consider this. So I have E, B, C, B. They are all correlated. Set 1. So correlated gamma rays. I am not talking about energy. I am just talking about whether they are in coincidence or not. Correlated, not no energy information. So E, B, C, B. Okay. Next.
A or F.
Set 2.
A or F.
A. Okay. Set 2. F.
A.
F. A. B. So here number is 4. Here number is 3. See? F. This is F. Then A. Then B. This is coincidence. Okay. Next. G. C. B. G. C. B. Again number is 3. So maximum I think here we can have 4 correlated numbers in this example. Just to give you an idea. Similarly, you see, I can have F, D, C, B. F, D, C, B. F, D, C, B. Or if I use this branch, F, A, B, then again I will have 3. So you can say overall in this particular example, overall multiplicity is approximately 4. 3 to 4 roughly. See, in this example, we have got 4 correlated gamma rays obtained in 2 different ways. Again, 3 correlated gamma rays obtained in 2 different ways.